Okay, so now I'm going to talk a little about the unit operations in the DWSIM. We will take a look at the basic unit operations, then I'll show you a little bit of each reactor model, then talk a little bit about the advanced unit operations and the logical blocks that you can add to the flowsheet. Okay, so let's add let's create a new simulation. I'll add methane and Ben Robinson. Here on the right side of the screen you can see the list of unit operations and other components that you can add to the flowsheet. We have the absorption column, which is a model for rigorous simulation of absorption columns. Okay, I'm going to show you in a separate course specific to the rigorous columns. You have the adiabatic compressor, which can be used to simulate a adiabatic compression process, as the name implies. So let's create some sample conditions. For instance, if you want to increase the pressure of this gas stream to, say, 100,000 Pascal, 500,000 Pascal, it will calculate the power required given this efficiency for the compression process. The expander works the opposite way. You can use it to generate energy from a high pressure stream through an expansion process. You can define the outlet pressure or the pressure decrease or the power that this expander will generate, or even the power from the specified on the energy stream. But I think that the expander doesn't work with this specification, with this calculation mode. So let's specify the outlet pressure and we will see how much power it generates considering this efficiency. Pretty simple. The pump, we already know it from the basic 1 course. The compound separator, it can be used when you have a separation process that doesn't fit on any other model in the DWSIM, or when you don't know how you will separate the compounds from the inlet stream, and you just want to make a physical separation of these compounds. So you can specify how much of each compound goes to the outlet stream 1 or to the outlet stream 2. And the DWSIM will calculate the mass and the energy balance in this block. Okay, so here we specified that all the propane goes to the outlet stream 1, and you will see that there should be no propane in material stream 12 here. See, you can specify percent mass flow, percent molar flow, or absolute mass or molar flow for each compound in this unit operation. Okay, here we have a reactor, the continuous stirred tank reactor. You will have a separate course for the reactors. This controller block is a logical block. I'll talk a little about it in a separate course. Conversion reactor 2. Here is a cooler. The cooler will be used when you need to remove energy from a stream and you don't know how, but you just want to know how much energy will be removed from the stream in order to achieve a specified temperature at the outlet stream. Or you can specify the heat removed from this stream, say, and DWSIM will calculate the outlet temperature of the stream. The heater is exactly the opposite. It is used when you need to increase the temperature of a stream and you want to know how much energy will be required in order to elevate the temperature of this stream. So let's say that we need to increase the temperature in 50 Kelvin, and the DWSIM will calculate the energy required to do so. You have a lot of options to calculate the outlet temperature and the heat added to the inlet stream, and you will see that the outlet stream will contain the results of the calculation. The energy stream will hold the power required to elevate the temperature, and for the cooler we have the same. It will hold the value required to cool down the inlet stream to the specified outlet temperature. Let me remove these unit operations. The distillation column, we will talk about it later. Energy cycle block, we'll talk in the logical block section. The energy stream, we already know it. The equilibrium reactor, we will see later. The filter unit operation works only with solids. It is used to calculate the pressure drop across a filter, giving some parameters. It is not much used, but should be straightforward for those who want to use it. Okay. The flow sheet unit operation works by loading an existing flow sheet and calculate it inside the main flow sheet. You have a sample in the DWSIM which shows its functionality. In this sample we have a existing flow sheet loaded inside this block, which contains a flash separator, and it is linked to these streams. When you click to solve the flow sheet, the DWSIM solves the internal flow sheet and calculates the stream. Okay. Normally it is used to calculate complex flow sheets, and when you have a lot of unit operations in a single block, then normally we use this unit operation to keep things organized in our flow sheets. Okay, so let's go back to the gas liquid separator. It is used to separate vapor and liquid phases from a material stream. If you have a stream which is in vapor liquid equilibrium, this unit operation will separate the phases into separate streams. Okay, so here we have the vapor phase from this stream, and this other stream will hold the liquid phase from the inlet stream. If you have two liquid phases, you should see something in this stream too. You can override the separation temperature and pressure, but for that you will need to connect an energy stream, so the DWSIM will calculate the energy balance on this stream, on this unit operation. Okay. We also have a heat exchanger when you need to calculate the heat exchanger between two streams. Let's say that you have a stream 400, 200, and you want to calculate both outlet temperatures, and you know the overall heat transfer coefficient and the heat exchange area, and the DWSIM should calculate. Heat exchanger. It will calculate the temperatures of the outlet streams, the heat exchanger, and the thermal efficiency of this exchanger based on the maximum possible heat exchange according to the specification of the inlet streams. Okay, you have a lot of options. You can use the geometry of Shannon tubes heat exchanger. You can input the geometry here, and the DWSIM will calculate the pressure drop and the overall heat transfer coefficient. You have a sample if you want to see how it works. It's called the heat exchanger sizing and design. Okay. The piping segment, we already worked with it in basic 1 course. The PFR, we will see it later. Python script 2, recycle block 2, shortcut column. It is used to do a quick calculation to specify a separation column. you have one feed stream, one distillate stream, bottom stream, the condensate duty, and the reboiler duty. Okay, and usually the feed stream is in equilibrium. Okay. And you must define the light key, which is the lightest component in the mixture, and the heavy key, which is the heaviest component, and the amount of the light key in bottoms, the amount of heavy key in distillate stream, the reflux ratio, and it should calculate just fine. Okay, but sometimes if you specify some unrealistic parameters, it will not calculate some properties like the actual number of stages and so on. So let's change a little bit the parameters of this column. Yeah. Now you have the number of stages. This is not a difficult separation, as we can see from the number of stages which was calculated. Okay. The solid separator works like the flash vessel, the flash separator, but it separates the solid phase from a liquid solid stream, and you can specify the separation efficiency for both streams. Okay. We also have the mixer, which can be used to mix up to 6 streams. We also have the tank. The tank just calculates the residence time of the liquid fluid according to the inlet flow rate, and we've already worked with it in the basic 1 course. The splitter can be used to split a material stream up to 3 streams. You can specify the split ratios or specify the flow rate of up to 2 outlet streams, and DWSIM will calculate the mass balance according to your specifications. Okay, you can specify the mass or molar flow if you decide to specify a flow rate, and the split ratios if you choose to do so. Okay, and finally we have the valve. The valve can be used to calculate an adiabatic expansion, isenthalpic expansion, sorry, for usually for a gas stream. So you can see how much the temperature drops, for instance. You can specify the pressure drop or the outlet pressure for this unit operation. Okay, let's choose something close to atmosphere, and you will see that it calculated the temperature drop according to the pressure and enthalpy flash calculation. Okay, this is a isenthalpic process, so there is no need to connect an energy stream to the valve. Okay, so that's all for now. We will talk a little bit about the other unit operations in a later later videos. Okay, bye bye.